All right, students, so we're going to do a video on Euler paths and circuits. So this is Leonard Euler. I'm not exactly sure what he's wearing on his head, but I guess that was the style back in the 1700s. He was born in 1700 something and died in 1783, I believe, something like that. Anyway, his name is all over mathematics. It's on your calculator. E is named after Euler. So it's pronounced Euler. So we're going to talk about Euler paths. He did quite a bit in graph theory. An Euler path is a path that uses every edge in a graph with no repeats. Being a path, it does not have to return to the starting vertex. So for example, if we have, say, this here, we could start here at this point D, go around, and come to C. Or let's take a look at another one. Say we start at C. We could go from C to A to B, B back to C, and then C to D. So that's an Euler path. Basically, we're using all of the edges, but only using them once. We're not retracing our steps. Here's another one. We could look at this one. Oh, I just wanted to put the arrows in, make sure we know where we're going. So say we started here at A, in this graph that kind of looks like a, hamburger. We could go from A through B to C, back to A, and then back to C. So that's an example of an Euler path. An Euler circuit is a circuit. A circuit basically uses every edge in a graph with no repeats. But a circuit, it must start and end at the same vertex. So let's look at an example. We could start at A and then go to B, then go to E, go back to B, over to C, to D, to E, back to A. So that's an Euler circuit. We've only used each path once, and we started and finished at the same place. Let's think about this. So that's an example of an Euler circuit. What are the degrees? So if we remember what degrees are, and we'll talk about degrees in a second, degrees of each vertex, that's how many edges are leaving the vertex, right? So this is a degree 2. This is degree 2, right? We have 2 edges leaving that one. This one has 4 edges leaving, 1, 2, 3, 4. So does this one, 1, 2, 3, 4. And remember, an edge doesn't have to be a straight line. It can be a curve. This one has 2, and then this one has 2. So we're going to come back to this because this is very important. Notice that all of these degrees are actually even. So here's a definition of an Euler path and a circuit. Well, here's a fact about an Euler path or a circuit. These are actually theorems. A graph has an Euler circuit if and only if the degree of every vertex is even. So if we go back to that one, this is an Euler circuit because all of these vertices have even degrees. So that's the only way you can get an Euler circuit. Otherwise, it doesn't work. A graph is an Euler path, like the ones we looked at earlier on, if and only if there are at most 2 vertices with an odd degree. And we're going to look at an example of that. And remember, here are degrees, right? The degree or valence of a vertex is the number of edges meeting at that vertex. It is possible for a vertex to have a degree of 0 or larger. So it's just the number of edges coming into that vertex. So let's take a look at this graph here. That's the Big Dipper. How many degrees do we have at each node or at each vertex? Well, there's only 1 here, and then there are 2 edges coming into this one. That's 2, and then 2, and then 2, and then 3, right? 2, 2, 2. So let's write those down. So these are all of the degrees for each vertex. So this is an example of a graph that has 2 odd vertices. So we can't have an Euler circuit here, meaning we can't start and end at the same place, but we could have an Euler path. But I wanted to add one special thing about Euler's, that theorem that we just saw. If, and here's the corollary, if there's an Euler path with two odd degrees, it must start and end at one of the odd vertices. So let's think about this. So there are only two odd vertices here. There's 1 and 3. So that means our path has to start here or here. We can't start our path here. We can't start our path here, here, here. So let's look at an example. So if I start here at 1, I could go to 2, and then all the way over here, and back around. And notice I've ended here at 3. Let's see that again. Yeah, so I just ended right there. Now I could also start here at 3, and say I go down here to 2, and then I can loop myself around, but I'm going to end at 1. So this is kind of a neat thing, and like when we're playing some of those video games that we've played, that is kind of what happens. So if we see, like, you'll notice, like when you're doing those video games where you can't overlap the lines and things like that, it's really just an Euler path that you have to end or start at an odd vertex. So here's an example of no Euler path, right? This is the one we looked at the very start of class, that you couldn't find a path that worked. And the reason is because it has 4 vertices that are odd. So there's no way for you to actually solve this problem with an Euler path, right? There's no way to like make a path without retracing your steps. So anyway, those are some examples of Euler paths and circuits. I hope this helps, and please let me know if you have any questions.